in the last lecture we defined a basic feasible solution. Then we also said that there can be degenerate and non-degenerate basic feasible solutions. We found a upper bound on the number of basic feasible solutions that an LPP can have. And then finally we said that if feasible region, if there is a feasible solution to a LPP, then there will always be a basic feasible solution. Actually, I showed you how we could construct a basic feasible solution from a given feasible solution. So we further carry on the process of developing the simplex algorithm. So the first result that I would like to discuss now is that how do you, given a basic feasible solution, we want to move on to a better one, in the sense that the objective function value should improve. So first I will give you the method for moving from one basic feasible solution to another. So moving from one basic feasible solution to another basic feasible solution. So this starts this will give us the beginning of the simplex algorithm, the iterative procedure that we will follow for solving a standard form of linear programming problem. Okay. So suppose let consider be a basis, and without having to repeat every time, I will just always be referring to the standard linear programming problem that I defined as problem 3 in the earlier lectures. So consider B a basis and let x be 0 be the corresponding basic feasible solution. So here again I have renumbered the variables and the columns, so that the first m variables correspond to the basic variables and the last n minus m variables correspond to the non-basic variables. Okay, so the corresponding basic feasible solution. Now see, our notion, when we say that B is a basis, and this the required mathematical background I will try to sum up in one lecture, which will come in the beginning of this course, so that you have the definitions and the whatever mathematical background I am assuming in my lectures, I will try to give that in the first lecture. So B is a basis, which means that since B is a basis, this implies that any column of A can be expressed as a linear combination. Yeah, this concept I have used in the earlier lecture also, but it doesn't harm to repeat it again and again. Expressed as a linear combination of the basis columns, right. So this means that there exists, therefore there exist scalars Yij, I varying from 1 to m. These are specific to the column Aj. There exist scalars this for a column Aj such that j does not belong to Ix, or I could have said that Aj is not a column in B, right. So there exist scalars Yij for a column Aj such that Aj can be written as summation Yij Bi, I varying from 1 to m. Okay, so I express Aj as a linear combination of the columns of this. This I can rewrite as, this expression we can write as minus Yij Bi summation I varying from 1 to m plus Aj equal to 0. So take this expression as 1. Okay. Also this is a basic feasible solution. So I have that since xb0 is a basic feasible solution this implies that summation xbi bi, I varying from 1 to m is equal to b, the right hand side. Right. And then again I will do the same trick that I did earlier. I will multiply this by theta and then add to this equation. Okay. So, this, if I call this as 2, then I am looking at the expression 1 into theta plus 2, which gives, and it gives me, and it gives us summation xbi plus theta yij bi, I varying from 1 to m is equal to b. So, it is almost the same way of constructing. So, here I am using the fact that my aj is a linear combination of the columns of b, and so therefore, there is a set of scalars, not all zeros, because if they are all zeros then aj would be 0, but certainly aj is not a 0 vector. So, 0 column. So, therefore, I have this, the scalars yij exist, and then I rewrite this expression in this way, multiply it by theta, add it to this equation, and I get this. Okay. Sorry, there is something missing. Yeah. So, I should have, because there is a plus. So, there will be plus theta times aj, then it is equal to b. Okay. So, let me call this as 3. Now, you see that if you look at, I have these scalars which are used for combination of the columns of b, and then I have theta here. So, this could be called a solution. I am not calling it a feasible solution, because I do not know whether all these numbers are non-negative. So, because that depends on theta and it depends on yij's, right. So, here of course, let us say I specify that theta is positive or non-negative. Of course, non-negative does not make any sense, because I am trying to construct a new solution. So, let us take theta to be positive. In that case, yij's could be large enough numbers, so that this expression need not be non-negative. Xbi's are non-negative, theta is positive, but the signs of yij and the values of yij, they matter, right. So, therefore, and since we are trying to construct a new feasible solution, so I require that these scalars must be non-negative. So, here if all yij's are, now again please, there was a minus sign here, yes, I could see. So, therefore, this has to be minus, yeah, okay. So, in any case, yij's can be both positive and negative. So, let us see, if all yij's are less than or equal to 0, then of course, the signs of these numbers will be non-negative, and so this will be a feasible solution. If all yij's are less than or equal to 0, the solution in 3 is feasible. It cannot be basic feasible solution. Why? Because I have m columns here and I have another column here. So, total number of columns is m plus 1. Since the rank of the matrix A is m, it follows that m plus 1 columns cannot be linearly independent. Therefore, this is at most, if all yij's are less than or equal to 0, the solution in 3 is feasible, right. We will deal with this case later. We will deal with this case later. So, now let me take the situation or consider the situation. So, consider the situation that some yij's are greater than 0, okay, some yij's, and that's simple, or at least one of them is positive, right. So, in that case, I require that xbi minus theta yij should be non-negative, which implies that theta is less than or equal to xbi upon yij, right, when such that Yij is positive. Okay. For negative ones, I don't have to worry about the sign. It's only about whenever Yij is positive, I have to worry about the sign of this term, and so I put a condition on theta that theta must be. So in that case, we say that we choose theta to be minimum of xbi upon Yij, and let us say that this is equal to xbk, or okay, I'll use the xbr upon Yrj. Okay. So that means now you see that the relationship. So theta, if I choose theta to be this value, then what happens to the value of this term xbr minus theta Yrj? See, if I substitute theta equal to this, then you see this becomes 0. So what has happened is that your rth basic, the new value of the rth basic variable, if I want to, has become 0, right? And this theta value, this is certainly, I am choosing this, this is non-negative, because I don't know about the value of xbr. It could have been a degenerate basic feasible solution, and therefore xbr could have been 0, but does not matter. Whatever it is non-negative number. I am dividing by a positive number, so again the ratio is non-negative. Okay. Theta is positive here. So now what have I managed to do? By making this choice of theta, I have managed to make one of the basic, the new value of the new basic variable equal to 0. So it becomes non-basic. A non-basic variable, originally aj, because aj was not a basic column, but now I have given it a value theta, right. This is how we are now used to reading the solution. The coefficients which are the coefficients of the columns which you use in expressing the system of equations, they become your solution, right. So the new solution, if you look at it, this is, let me call it x hat. So x hat I or x hat bi, because again this is the same index, this is equal to xbi minus theta times, or if you want me to write the value here of theta, this is xbr upon Yrj into Yrj. This is the new value, and you see that this is valid for I varying from 1 to m, I not equal to r, because for I equal to r it is 0, right. And you have that xj hat is your xbr upon Yrj. So you have m minus 1 positive or non-negative values here, and you have another non-negative value here. So you have m of them. Now of course, since our idea is to move from one basic feasible solution to another, so obviously we would want that the corresponding columns here should be linearly independent, and this again is the theorem from linear algebra, from a theorem from linear algebra. We have that the new set of columns, that the new set of columns, and this new set is actually B1 to Bm and Aj, and then minus Br, right. So this is a new set. The columns B1 to Bm, but Br is missing, and then Aj. Set of columns is also linearly independent. Okay, the theorem in linear algebra says that if you have a set of linearly independent columns which forms a basis, then I express a non-basic column in terms of the basic columns, and then I can replace one of the basic columns by the new column, provided that the coefficient used in expressing Aj as a linear combination of B1, B2, Bm is non-zero. And remember, what was our Yrj? Our Yrj was because I said that when you express Aj as a linear combination of the basic columns, then this is I varying from 1 to m. So Yij is the coefficient of Bi. So Yrj is the coefficient of Br, and we assume that Yrj is positive. Okay. So we did this ratio for all Yij's which are positive. So therefore, and took the minimum. So Yrj is a positive number. Therefore, linear algebra theorem says that if you replace the corresponding basic column here by Aj such that the coefficient used here is positive, that is non-zero. Linear algebra does not have to do anything with the sign of Yrj. It is here that we are concerned with the sign of Yrj, because if Yrj is negative, this number will become negative, right, or non-positive, because XBR is non-negative. So we want to go from one basic feasible solution to another. Therefore, we need the sign of Yrj to be positive. Okay. So then this is a linearly independent set, which implies that the new feasible solution is in fact a basic feasible solution. So we have achieved what we set out to do, that is to construct a basic feasible solution from a given basic feasible solution, and what we do is we replace one of the basic columns by one of the non-basic columns. Okay. Now this is not enough, because we want to improve the value of the objective function. So we want to say that we should have, so we need two things. We need to say whether a given basic feasible solution will give us the best value or not. If it does not, then I should be able to move from that basic feasible solution to another, such that the value of the objective function is improved, right. And of course, the third question that some of you, it may have come into your mind, is that why am I concentrating on basic feasible solutions? And that question will get answered maybe after 2 more lectures, or in the fourth or fifth lecture, whatever it is. So right now I am just constructing, I am developing the theory with respect to basic feasible solutions, and in a short while it will be clear why we are doing that, right. Okay. So now the next move is to move from one basic feasible solution to another, and in the process improve the value of the objective function, right. Let me just keep a tab on this thing. So now our new basic feasible solution that I obtained, so this is xb hat I is xbi minus xbr upon yrj into yij, right, and xj hat is xbr upon yrj. Move from a basic feasible solution to another, and also improve the value of the objective function. Okay, so the key word here is now improve, right, and we can quickly recall that I had a basis, I replaced one of the basic columns by a non-basic column, then and I did this by making the value of the new value of the basic variable corresponding to the column I am replacing 0, so that it gets the status of a non-basic variable, and the non-basic variable I made the value as positive, so that it becomes a basic variable, right. So this is what we are doing. Okay, this is your new feasible solution. For the original one, for the basic feasible solution xb0, the value of the objective function is equal to cbi and then b inverse b I summation I varying from 1 to m. Yeah, remember, because our since our solution xb is given by b inverse b, remember, because b is a non-singular matrix and we put all other variables equal to 0. So this is our basic feasible solution. The non-negative ones, the others are all zeros. So, and these are the corresponding coefficients of the basic variables in the objective function. So, this gives me the value of the objective function, which in short I can write as B inverse B. Now, it is understood here that C B is a row vector. I can write the transpose, and then it becomes tedious writing it so many times, right. So, now consider the, so let us compute the value of the objective function. Objective function for the new basic feasible solution. So, here the coefficients remain the same, and for the except for the this thing, and you see that since XBR hat is 0, I can include that in the summation. What I mean to say is that will be equal to summation, I will write as CBI XBI minus XBR upon YRJ into Yij, right, I varying from 1 to m. So, I do not have to exclude the Rth term, because anyway this number is 0. So, the contribution of the Rth term to this sum will be 0, therefore, I can keep it, and that will be convenient because I want to read it, and plus it will be Cj into XBR upon YRJ, right. This is my new value. So, let us rewrite it to get the condition as to which basic feasible solution I should move to in order to improve my value of the objective function. So, if you now look at this summation CBI XBI, that is my old value of the objective function. So, that will be simply, so if I write Z hat as my new this thing, then this is equal to Z, because CBI XBI is my new old objective function. Then this is plus, you see, Cj minus, and now look at this. Here XBR YRJ is something which is common, then you are multiplying CBI with Yij. So, you are summing up over I. So, if I quickly rewrite this, this is summation CBI Yij, I varying from 1 to m. This into your XBR upon YRJ. This is the expression, right. So, you see this quantity is specific to your, because the Yij's were the scalars used for expressing the jth non-basic column in terms of the basic columns. So, these scalars are specific to your jth column. So, then CBI are your basic coefficients, basic variable coefficients. So, this becomes something specific to your jth non-basic column, right. So, this I can write as Z plus Cj minus Zj into XBR upon YRJ, right. So, Zj is something which is equal to this. So, you see the change in the, so very nice way of expressing the change in the objective function value when you go from one basic feasible solution to another. And obviously, if you want the value, since we are considering a minimization problem, and once I give you the condition for minimization problem, you can immediately write down the condition for a maximization problem. So, there is no problem there. So, here if my the LPP is of the minimization form, then I need this to be less than or equal to 0. In fact, if I want it to improve, then it should be less than 0, but you can say less than or equal to 0, right. This is something which is non-negative. So, if I want Z hat to be less than Z, then Cj minus Zj should be less than or equal to 0. So, therefore, what is being said is that, see here, I arbitrarily chose, given a basis B, I arbitrarily chose Aj. The only condition was that I will replace Aj, I will bring in Aj into the basis and remove one of the basic columns here. You are replacing a basic column Br by the non-basic column Aj, provided Yrj is positive, and then the R has come from the fact that this ratio XBI upon Yij was minimum. So, therefore, the R came from that, right. And so, you got that means you replace Br by Aj such that you get a new basic solution which is feasible. First is that is the condition, and then Cj minus Zj is also less than 0. Then in that case, when you replace Br by Aj, your value of the objective function will go down. That is z hat is equal to z plus Cj minus Zj into xbr upon yrj. So, if this is negative, and this can be non-negative, so it can be 0 or positive. So, in any case your z hat would be less than or equal to z if you replace Br by Aj, provided you get a new basic feasible solution and this condition is satisfied, right. So, then we say that Br comma Aj is an improving pair if it satisfies all the three conditions. That means your Yrj is positive, and then you get a new basic feasible solution by replacing Br by Aj, which means that you are only replacing that particular basic column for which this ratio is minimum, so that you end up with a new basic feasible solution, and then Cj minus Zj is also less than 0. In that case, this is an improving pair. And so, the next step would be, and as you can see that this may not be, there may be more than one j for which this is less than 0, and in that case it is not, I mean Aj may replace a particular basic column, may get replaced by more than one non-basic column and still improve the value of the objective function. So, therefore, this would be this is not a unique pair, this can be more than for a given basic column to be replaced by a non-basic column, the choice may not be unique all the time. M such pairs for a given j, for a given non-basic column, m such pairs at most, right, upper bound. So, there can be m such pairs, and then we have n minus m non-basic columns, n minus m non-basic column, right. So, you might say that we have how many, m into n minus. So, the total number of such pairs that you can consider. So, total number of such pairs can at most be m into n minus m. Okay. Now, let us come to the second question. Since we are wanting to minimize, obviously you would want to make the maximum improvement in the objective function value, and for that what would you need to do? See, here the improvement is product of Cj minus Zj into xbr upon yrj. So, you can say in other words that this is the level at which your jth basic variable is entering the basis, right, and this is the rate of improvement in a sense, because the total improvement is Cj minus Zj into the value, the level at which the variable is coming into the basis. So, this is the total thing. So, now if you want to find out what is the best possible improvement in the value of the objective function, you will have to do this exercise. That means, you will have to compute this and this for all the m into n minus m pairs, right, to get the best improvement. But then that gets to be very inefficient, because your n, a reasonably sized linear programming problem can have a few hundred variables and a few hundred constraints. For example, this may run into 1500 variables and let us say 400 to 500 constraints, then this number is very large, and if you have to compute this quantity for each of these such pairs, then the algorithm will become very inefficient. So, at least that is not done. The idea is that you should be able to move from one basic feasible solution to another such that there is some improvement. If you stick to that, it has been, and of course, later on we will discuss all these aspects and show you that these things work. You do not really have to go for the best improvement, and because one tries to strike a balance between the improvement in the value of the objective function and the amount of work that has to be done. So, the two things are very, the balancing is very important, and that is what makes the algorithm efficient. Okay. So, this is what we have covered so far. Okay. Now, immediately you can see that from this equation you can derive the optimality criteria. So what we are saying is, and again it will not be, so the next thing I am going to talk about is optimality criteria. This is what is needed to determine whether a given solution is an optimal solution or not. So we definitely need this kind of thing, and because if we have this optimality criteria, then it will help us to stop the algorithm, because it will tell us that there is no more improvement possible, and therefore you stop, right. Okay. Now what we are going to, again I am trying to motivate how the optimality criteria comes about, and you see that here what is happening. If you cannot find a j for which Cj minus Zj is less than 0, right, then what we are saying here is that from this basic feasible solution B, or from this basic feasible solution that we have, if at this point I cannot find any non-basic column for which a Cj minus Zj is less than 0, then I will stop here and I will say that my xb comma 0 is a basic feasible solution. Okay. This is just a claim, I need to substantiate it, because all right now I have said is that given a basic feasible solution, if I cannot find a non-basic column such that Cj minus Zj is less than 0, then all I am saying here is that from the given basic feasible solution, I cannot make a move to another basic feasible solution such that the value of the objective function improves. This is the only claim I am making, but we will be able to show you maybe in after another lecture that this is enough. This condition is sufficient. That means if I have a basic feasible solution and such that I cannot find a non-basic column for which the corresponding Cj minus Zj is less than 0, then I should stop, and my current basic feasible solution is an optimal solution. Okay. So this is what we want to now start proving. So the optimality criteria is that we say that if for a basic feasible solution, so I am just continue to write it as this, saying that we have renumbered the variables and so on. For a basic xb0, if Cj minus Zj are less than or greater than or equal to 0 for all j, then xb0 is an optimal solution for LPP 3. Okay. And I will set about trying to prove part of course this condition. So for a basic feasible solution, if all Cj minus Zj's are non-negative, then this is then xp is an optimal solution. Okay. Now from the computation you see that here, yes, let us look at the computation. For a basic variable, I wanted to show you that computation. So you see, if you want to compute the ZBI, this will be CB B inverse AJ. Now AJ for the ith basic variable is BI, then B inverse BI is EI by our definition, right. B is the basis matrix, so this is the ith column and this is the inverse of the basis matrix. So B inverse BI will be EI, and therefore when you multiply this with this, it will be the ith component only. So CB, actually I remember I write this, even though this is a column vector, I am writing this as a row vector. So I am not writing the transpose here anyway. So CB, this is the m dimensional column, this is the m dimensional. So the product would be simply the ith component of the vector CB, the basic variable. So therefore for a basic variable, the ZBI reduces to CBI, and hence when you want to compute CBI minus ZBI, this will be CBI minus CBI, which is 0. So for a basic variable, the relative cost is 0. And of course we will spend some more time in interpreting these things in detail, but right now, as I said, that if you want to say that this is the rate at which the value of the objective function will improve corresponding to the jth non-basic variable, then what this says is that for the variables which are basic, the rate of improvement is 0, because whatever improvement was possible was done, so no more. So therefore, for the basic variables, the coefficient, the numbers or the quantities Cj minus Zj's are all zeros. So therefore, when I say this, that this is an optimality criteria, and it actually refers to the non-basic variables, and it says that for all non-basic variables, your Cj minus Zj should be non-negative. For the basic variables, the Cj minus Zj's are all non-negative. So now suppose, and therefore I can state this as a condition for all j's, right. So let us look at this now here. This says that Cj minus Cb B inverse Aj are greater than or equal to 0 for all j, which means that Cb B inverse Aj is less than or equal to Cj for all j. Let x be any feasible solution, let x be any feasible solution. So that means all its components are non-negative, which implies that xj is greater than or equal to 0 for all j, and Ax is equal to b, right. So if I multiply each of these equations by the corresponding xj and add, see this quantity is common, so therefore I can say that therefore Cb B inverse summation Aj xj, j varying from 1 to n, is less than or equal to Cj xj summation j varying from 1 to n. The inequality does not change because I am multiplying by a non-negative number on either side. So this is what you have. Now this from your, since x is a feasible solution, this summation adds up to the vector b. So therefore, which implies that Cb B inverse b is less than or equal to summation Cj xj, j varying from 1 to n, and that gives you the result, because this is the value of the objective function. Remember, your basic feasible solution is b inverse b. This is the cost coefficients corresponding to the basic variables. So this is your objective function for the basic feasible solution xb0, and this is the cost for the x to be any feasible solution. So what are we saying here? We are saying that if x is any feasible solution, then the value of the objective function is always higher than the value of the objective function for the basic feasible solution xb0, for which this condition holds. So you see the simplification is evident here. So therefore this implies that the objective function value for the basic feasible solution, xb0 is the smallest. Among all feasible solutions, right, and therefore this is a valid optimality criteria. That is, if a basic feasible solution satisfies this condition for all j, then we can stop the algorithm there, and we will say that the current basic feasible solution is an optimal one. Okay. Now, a lot of things can be derived from here. For example, so what have we shown? We have shown that a basic feasible solution is an optimal solution. That is all. But I have not claimed, and of course, the questions can be asked that you may have a basic feasible solution, but then this condition may not hold. If this condition does not hold, then we said that we will move to an optimal, because if there is some Cj minus Zj which is less than 0, then I can move to a new basic feasible solution and improve the value of the objective function. So this goes on, but then the question asked would be, that is, right now we have not established in a comprehensive way that a linear programming problem will always have a basic feasible solution as an optimal solution. So I still have to do some more work, but right now what we have concluded here is that if you have a basic feasible solution and it has this property, it satisfies this condition, then your basic feasible solution is an optimal one. Okay, so we have proved this. And now just to make the things more interesting, let me just also recount a lemma here, which is simple, and that again gives you some insight into the. So the lemma says that given a basic feasible solution x to LPP3, given a basic feasible solution, a cost vector C can be found such that x is the unique optimal solution with respect to C. Okay, one needs to understand, and maybe the implications will also become clearer as we go along with the course. So what we are saying is that if you have a basic feasible solution, then you can always find a cost vector C such that this basic feasible solution is a unique optimal solution with respect to the C. Okay. And the construction is interesting, and therefore it will give you an insight into the theory of LPP and how we look at how we construct this simplex algorithm. So let's say define, so proof. So let define Cj as 0 if j belongs to Ix. So again I am using the same notation. That means put the coefficient of cost coefficient Cj equal to 0 corresponding to the basic variable which is positive, right. Ix is the collection of indices corresponding to x for which the basic variables are positive. So if basic variable is positive, then put the corresponding cost coefficient as 0, and 1 if, or okay, to be no, I'll redefine because this will not be good enough. And you see, so that one you can also learn by these kinds of small mistakes, in the sense that if j, if if aj belongs to B, so I want to do it for the whole basis. It will not be enough to, because my basic feasible solution may be degenerate. So then I need to define. Okay, so I have to say that Cj is 0 if aj belongs to B, and is 1 if aj doesn't belong to B. So this is my definition of a cost vector, right. And now, so obviously with this the cost function, okay, so if you have this cost coefficient for corresponding to the basic feasible solution x, then we are saying that so this implies that x is optimal for the corresponding LPP. Yes, okay, let us spend a few minutes on this. Yes, why is it optimal? See, I have chosen the cost coefficients such that the cost coefficients are 0 if the variable is basic variable, and the cost coefficients are 1. If now, since your LPP requires that the variables are non-negative and Cj's are all non-negative, you can immediately say that, see, yeah, since, okay, what I'll say is that is optimal because C transpose x, which is 0, is less than or equal to C transpose y for all y feasible. Yes, just think on it for a few minutes. What we are saying is that Cj's are non-negative, your variables are non-negative, so this number cannot be, has to be non-negative or positive, C transpose y, for any feasible y. And for C transpose x, I know the value 0 because I have chosen the c's to be 0 whenever x is a basic variable, and when x is non-basic then the variable has to be 0 and the corresponding coefficient is 1, but does not matter. So, the total thing is 0. So, this is always less than or equal to C transpose y for all y feasible. Okay. So, therefore, this is optimal. Now, you want to show uniqueness. To show uniqueness for x, what do I need to say? That suppose, so to show uniqueness for x, I need to show that if there exists another feasible solution y, right, such that the two values are equal, then y must be equal to x. That is what we mean by uniqueness. Okay. So, if there is another feasible solution y such that C transpose x equal to C transpose y is 0, right. So, to show uniqueness for x, I need to show that if there exists another feasible solution y such that C transpose x is this, then y is equal to x. This is what I have to show, right. Okay. Now, since C transpose y is 0, this implies that yj is 0, remember, for aj not in B. See, my definition for Cj says that this is 1 if aj does not belong to B, right. So, since Cj's are positive and this objective function value is 0, this implies that yj must be 0 for aj not in B, because the corresponding C is positive. So, this is what happening, right, and therefore, this implies that y is a solution of the reduced system or in fact, I should be able to say yb, because I have put all yj's as 0 whenever the corresponding column is not in B. That means, for all the non-basic variables the yj is 0. So, if the reduced system, right, which implies that yb equal to B inverse B is equal to xb, and the non-basic variables are already the same by definition, because I have said that yj must be 0 whenever the corresponding column is non-basic, and this is non-basic with respect to the solution x that you had. So, therefore, y must come as the reduced from the reduced system B, yb equal to B, and so that says that yb is B inverse B, which is xb. So, the solution is unique. Okay, fine. So, this, after all this theory, let me just now take up an example and I will try to illustrate all these things, that means moving from one basic feasible solution to another, improving the value of the objective function, and demonstrating the optimality criteria, right. Okay. So, I write the example here. So, this is the LPP, minimize z equal to 2x1 plus x2 minus x3 subject to x1 plus x2 plus 2x3 less than or equal to 6, x1 plus 4x2 minus x3 less than or equal to 4, x1, x2, x3 greater than or equal to 0. I will convert this to a standard form. So, the standard form is would be minimize 2x1 plus x2 minus x3 subject to x1 plus x2 plus 2x3 plus x4 is equal to 6, x1 plus 4x2 minus x3 plus x5 is equal to 4, and xj's are greater than or equal to 0 for all j. Okay, this is my standard form, and starting immediately without checking anything, I can immediately say that these two columns are linearly independent, because this is E1, this is E2, so they form a basis for the column space. So I'll use my starting basic feasible solution given by the columns A4 and A5, which means that I put x1, x2, x3 equal to 0, and I immediately read my basic feasible solution as x4 is 6, x5 is 4. So choose B as A4, A5, which is nothing but E1, E2, and so this is an identity matrix, right? And so here, and therefore your basic feasible solution, basic in the complete form, if you want to write, basic feasible solution is 0, 0, 0, 6 and 4. Okay, and so now I need to compute I want to check the optimality criteria, which means that I have to compute the Cj minus Zj's to see whether I can improve the value of the objective function or not. So what we will do is, here we will compute all the Cj minus Zj's for each of the non-basic columns, A1, A2 and A3, right. So now here things are very simple, because your Cb is 0, 0. The slack variables don't appear here, so therefore Cb is 0. If Cb is 0, which implies that all Zj's are 0 for all j, right, because Zj was Cb inverse B, Cb B inverse, Zj were Cb B inverse Aj. So if your Cb has all 0 components, everything is 0 here, right. Okay. So therefore your Cj minus Zj's are simply Cj's, and this we have to compute for the non-basic variables, so which is already known to us. This is C1, this is C2, and this is C3. So we see that C3 equal to minus 1 is less than 0. So your optimality criteria is not satisfied, and in fact, if we induct the third column into the basis, then we can improve the value of the objective function. And by the way, what is the current value of the objective function? See, remember, x1, x2, x3 are all 0. So the current value, this is this, and your z is 0. So the starting value here, z is 0, and we can improve on it, because I have this condition satisfied that C3 or C3 minus Z3 is minus 1, which is less than 0, right. So if I induct this into the basis, what does my basis become? So the new basis is and okay, yes. So how do I know which? So yeah. So the next question that has to be answered is, which of these basic columns A4 and A5, which of them will be replaced by this? And remember, for that what were we doing? So here before I write the new basis, since I am inducting A3, so that means I will write my A3 column is 2 and minus 1, and there is no problem, because my basis is identity matrix. So this is actually 2 times E1 minus 1 times E2, right. And remember, we use the positive Yij's. We use the positive Yij. There is only one positive Yij, the other one is negative. So there is no need to take the minimum, the ratio, and compute the minimum one among all Yij's which are positive. So this simply tells me that E1 will get replaced by, because this coefficient is positive, right, this is greater than 0. So this implies that the column A4 gets replaced by A3. This is it, right, and therefore your new basis is A3, A4, okay, which you can write in terms of this A3 is 2 minus 1, and A4 got replaced. So this is A5, 0, 1. Yeah, okay. Now I need to compute. Yeah, is it okay? Fine. Now you need to compute your new basic feasible solution. And if you can recall the formula, so what was the formula? xbi hat we said is xbi minus xbr uponyrj into yij. So we have all the numbers. So for example, here your new basic variables and your aj x hat j was xbr upon yrj, which we already know because this is 2, right? The yrj is 2 and xbr, what is the value of xbr? xbr is 6 because the value for the outgoing basic variable was 6. So your this thing is 6 upon 2, which is 3. So the new value, and this is actually your x3 hat. So the new value of the which was a non-basic variable x3 is now become 3, right? And what is the value of your this thing x hat b 2? This is the second basic variable, right? Remember, this was the first basic column, this was the second basic column. So x hat, this is equal to what was the original value of this thing was 6 minus xbr upon yrj is 3. And what is your yij? The corresponding this thing is minus 1 here. Remember, these are the yij's are the scalars I need to express the incoming column in terms of the old basis, right? So this is minus 1. So this into minus 1. So this becomes 9. So actually this value goes up, and these things also we will later on keep focusing on. See here, because in this equation you see these two are zeros, x3 became positive, so the value of x5 actually goes up. This is 4, so why is it showing 9? Sorry, why didn't somebody correct me? This is 4. Yeah, this is 4. So 4 minus 3, so this is 7. Sorry, this is the new value is 7. So your new basic feasible solution is 3 and 7. This, I'm just writing the basic value, but in the complete form, complete basic feasible solution is 0, 0, 3, 0 and 7. This is your new basic feasible solution, and of course you can compute the value of the objective function directly. New value of the objective function is equal to, yes, from the objective function you see only x3 is positive, x1, x2 are 0, it's minus 3, which is definitely better than what you had, what you started with. Z equal to 0, now it is minus 3. Yes, quickly, I'll just complete it now here. So minus 3 is less, the value has improved, and of course you could compute it by the formula that I gave you. Okay, so now we need to just quickly verify whether this is optimal or not, and if it is not optimal, then we will move on to a new basic feasible solution. But so whatever we discussed so far, I have tried to demonstrate that through this example, and now this is your basis and this is this. So I need to, what do I need? I need to compute my new Cj minus Zj's, and for those I need the B inverse. So let us see, if your new basis you want to call it B hat is 2 minus 1 0 1. So B hat inverse, now you should be familiar with this, that you can immediately, for a 2 by 2 matrix it's not a problem at all. This will be 1, this will be 2, and this will be minus 1, plus 1 and 0. Is it okay? Quickly verify. 2 0 this, and this will be half because the determinant is 2. So I divide by 2. So this is 1, then this is 0, this is minus 1 plus 1 0, and this is, so this is the inverse. This is the inverse, and therefore you need CB B inverse. Now what is your CB? CB now in this case is minus 1 and 0, because x5 has a 0 coefficient, x3 has minus 1, and this is there's a half here, 1 0 1 2. Okay, so let's quickly compute this. This is minus 1, so minus half, and this is 0 0, so that is 0. So this is your CBB inverse, and now only two non-basic columns. Well, x4 is there, a4 is there, but I'll quickly do it for a1 and a2. So a1, so if you want to compute c1 minus z1, right, hat you can say. So then c1 is 2 minus z1. z1 will be minus half 0 into 1 1. Yes, a1 is 1 1. This is your CBB inverse. So if you compute this thing, this is minus half plus half. So this becomes 2 plus half, which is positive, right? Then compute c2 minus z2 hat. So this is c2 is 1 minus minus half 0, right? And this is 1 and 4. So this again is 1 plus half. This is positive, and you need to do it for c4 minus z4 hat, which is equal to c4, this is 0, right, and minus minus half 0, and this is 1 0, which is again is half, which is also positive. So you have arrived at a optimal solution. That means the current basic feasible solution satisfies the optimality criteria, and the minimum value of the objective function is minus 3. So right now I have tried to show you that the algorithm that we will finally develop for these for solving a linear programming problem is an iterative method, and I have tried to show you how we will go from one basic feasible solution to another and improve the value of the objective function. And there is a stopping criteria also, that the algorithm will be able to stop. Now, able to stop, I have to still explain further, and we will talk about it in the next lecture. Okay.